Hey guys, Mr. Patterson here, checking in with section 1.2, talking about displaying quantitative data with graphs. In section 1.1, we focused on categorical data. In this section, we'll talk about quantitative data, just specifically about the graphs, and we'll talk more about quantitative data in 1.3. We have a few objectives we want to make sure we focus on here in this section. We're going to be making different types of graphs. We're going to be making dot plots and stem plots and interpreting them, describing overall patterns and any deviation from those patterns. Outliers, if they are clear, we're going to talk about them. We're going to talk about the shape of a distribution. And we're also, in addition to dot plots and stem plots, we're going to make histograms and interpret them. And lastly, we're going to compare the distributions of quantitative data. So hopefully by the end of this lesson, these ideas will be pretty clear to you. So dot plot's pretty simple, pretty straightforward. Basically, all we're going to do is we're going to take a number line on the horizontal axis, and we're going to put a dot representing each observation that we see. So horizontal axis, label it with the variable name, scale the axis from minimum to maximum, and then mark a dot above. Pretty straightforward there, but from that we can identify some key information about that distribution. This particular one happens to be from the number of goals scored by the 2012 U.S. women's soccer team. So we can see there are a couple really high values up here. There's a 13 and a 14. Those would clearly be considered outliers because they're far apart from the general data down here between 0 and 5. If we're examining the distribution, we kind of ask ourselves, what do we see, right? So when we're looking for that, we're looking for the overall pattern and any departures from that pattern. We're looking for the shape, the center, and the spread. And we want to talk about any outliers that might exist. Now, that idea of shape, center, spread, and outliers, we refer to that as your SOX. S for shape, O for outliers, C for center, and S for spread. Obviously no K, like in the normal spelling of SOX. But this idea of describing a distribution using SOX is pretty much guaranteed to be one of the questions on the AP free response. So you're going to see it a lot in class to make sure that we're ready for it. So how do we describe shape? Well, generally, we're looking at whether it is roughly symmetric or skewed one way or the other. We say it's roughly symmetric if the left side and the right side look kind of like each other. Not exactly, because that's uncommon, but kind of like it. We say something is right skewed if the values on the right side are much less than the values on the left side. And conversely, we say something is skewed to the left if the left side is much more spread out than the right side. If we look at these examples down here at the bottom, take a pause, try to see if you can figure out which one is which. But if we look at them, the dice rolls here, clearly roughly symmetric. Now again, not perfectly symmetric, but roughly symmetric, where most of the values are here in the center. Some values on the lower side, some values on the upper side. With looking at this next example, we see more values are on the high side, less are on the low side. So it's kind of like it's pulled out, it's extended to the left, so we say skewed left. And the opposite is true for the number of siblings here. We have most of the data points between 0 and 3, and then there's a couple on the high side there, skewed right. All right. So when we're comparing distributions, we want to talk about shape, center, and spread, but we want to make sure that we actually use comparing words. And that's enough to just say comparing words. So if we look at these two distributions here, looking at household size in South Africa versus household size in the UK, we would say, well, look here in South Africa. This clearly appears to be a skewed right distribution, whereas most people would probably say the UK is a roughly symmetric distribution. Are there any outliers? You'll notice we see this high point up here where there is a household in South Africa with something like 26 members. As far as center, if you're just asked to compare, then literally just do that. It is pretty clear to me that the median value for South Africa is going to be higher than the median value for the UK. So that's all we say. The center of the South African household size is higher than the center for the UK. As far as spread, we're talking about how spread out are they. The UK distribution is clearly much smaller than the South African distribution in their spread. If you wanted to, you could list the range. You could say the range for South Africa is 26 minus 3, or 23, compared to the range of the UK, which is 6 minus, looks like 2 there, and that's going to be 4. So that's from dot plots. Let's take a look at stem plots, also called stem and leaf plots. And like dot plots, every value, every observation is represented on the graph. When do you use one versus the other? Well, if you have a small range of data, then using a dot plot makes more sense. If the range is a little bit bigger, then use a stem plot. Both of them are for relatively small sample sizes. So how do we make a stem plot? We separate each observation into a stem and a leaf. The stem is going to be all but the last digit, and the leaf is the last digit. Unless it's a situation where you have really, really big numbers and you want to trim those values, and you can decide how you want to trim them based on the numbers that you have. All the stems go from smallest to largest in the vertical column, and don't skip any. So, for instance, if you have a lot of numbers in the teens, a lot of numbers in the 20s, and then you don't have any numbers in the 30s, but you have numbers in the 40s, you still have to write the stem of a 3. And then you write each leaf in the row to the right of its stem, and we usually separate them by column from, separate them by a comma, and they're written out in increasing order after the stem. And you always want to make sure you have a key, just to make sure someone doesn't misinterpret the values that they're looking at. If we look at this example here about how many pairs of shoes do you have, we see our data set here, and it's pretty spread out. We see, let's see, what's the smallest number? The smallest number appears to be 13, and our largest value looks like it's 57. So in this situation, we're going from 13 to 57, so our stems will be representing our tens place, and our leaves will be representing the ones place. So our stems go 1, 2, 3, 4, 5. And again, even if we weren't to have any value in any of these stems, we're still going to write that number. And then we're just going to write the numbers out in increasing order. So we see we have, first of all the numbers written out, but they're not in order. And then we just put them in order. So we see 1, this represents the tens place, and we have a 13, a 13, a 13, so there's 3 13s. There's a 15 and a 19. A 22, 23, 23, etc., all the way out. And to make it easier, we just put this key here. All right, say 4, vertical line 9, represents a female student who having 49 pairs of shoes, which is quite a few pairs of shoes. Now, sometimes the data is kind of bunched up, and if that's the case, we want to split those stems so that we can better see the shape. And also, if we're trying to compare distributions, we want to do back-to-back stem plots with common stems. So let's say we're trying to compare the females and the males in this situation here. So we have our female data of number of shoes and a similar data set for males. So the first thing we want to do is we want to understand what it means to split the stems, because we kind of can't see the shape of the males distribution too well because most of them are on the lower side. So we split them. And what I mean by splitting is that we're going to put 2 zeros, 2 1s, 2 2s, etc. The first 0 is going to take all values from 0 to 4, and the second 0 is going to take all numbers 5 through 9. And the same thing continues on. For the first 1, that's going to be the values 10 to 14, and then 15 to 19, etc., on and on. And we're also going to do this back to back so we can quickly and easily compare the distributions. For the males, we see it here. We have 1 value of 4. We have 3 values of 5, a 6, 4 7s, and an 8. And then we have just a few values above that as well. To go back to back, we're going to put the female distribution on the left side of the stems. But we're still going to put them in increasing order from the stem, which is interesting because we're going to be writing the numbers in increasing order from right to left, as we see here. Can't tell with the first 1 there, the first 13 values, but this 15 and then this 19. The 15 is smaller, so it goes closer to the stem. And it seems small, but the reason it's important is because if we start trying to cross numbers off to find the median from here, it would make our lives easier if we had the same kind of system that we're always going to do. But now that we have this in this back-to-back, we can clearly describe or compare the distributions. And it's pretty clear that the females have a larger center and a larger range. And we can look at that and to make that determination straight away. What do you think about the shapes? Take a moment, pause the video, and see if you can come up with that determination. As I look at it here, I see the males. They clearly have more values on the lower side, fewer on the upper side, so that's going to be a skewed right. The females, on the other hand, they're kind of evenly spread out. So most people would probably say that the females distribution is roughly symmetric. All right, and again, don't forget that key. Histograms. Histograms are another graph that we use for quantitative data. We use histograms if we have a large data set. So if we have 100 data points, 60 data points, 500, whatever we have here, if it's too large to represent every value in that stem plot or in that dot plot, histograms are the way to go. How do we make it? First thing we want to do is want to decide how wide are we going to make our class widths. So for instance, if our numbers are from 0 through 20, well, maybe breaking it up by 4s, so 0 to 4, 4 to 8, etc. That would be a pretty good idea. If our numbers are 0 to 500, maybe our class width is 100. If you're looking for a rule of thumb, generally somewhere about 4 to 8 bars is appropriate. If we have only 2 or 3 bars, it's hard to see the shape. And sometimes if we have, 15 bars or something like that, we can't see the shape either because everything is just too spread out. So it's kind of important to think about how wide should your bars be in the histogram. Then we're going to find the count or frequency for each one of those classes. And we could talk about them as counts or we could talk about them as percents. Either one is okay. But if you are going to end up comparing distributions, percents are definitely the way to go. Don't forget to label both axes, what's the variable that you're measuring, and put a scale as well. The bars should be touching because it represents a continuous variable that we're measuring there, as opposed to bar graphs, which the bars should be separated. If we look at this data here, the table representing, let's see, the percent of residents from each state who are born outside of the U.S., we see our class from 0 to 5, 20 people are in that data range. 5 to 10 is 13, et cetera, et cetera, et cetera. We can then use that to make our histogram. We can set it up. Notice we have our axes labeled, percent of foreign-born residents, and number of states. So these we're using the frequency, not the relative frequency, which would be if we had the percent of each one of those. And each one has a scale there. And then we just put the bars in. And again, if I were you, I'd take a moment to pause and describe this distribution. Clearly, this is a right-skewed distribution. To find the center, well, we could say, okay, we have 50 states that we're talking about here. So if I'm trying to find the median, it's going to be between the 25th and the 26th value. So that's clearly going to be in this second bar here because there's 20 here. Looks like 13 are here. So that's going to give us the 25th and 26th observation clearly in that bar. So we would say the median is between 5 and 10. The range, we can't be too specific, but we can say the highest is no more than 30 and the lowest is no less than 0. So the range would be 30 is how we would describe this. If we had the actual data, we could be more specific, but we don't, so we can't. Using histograms wisely. I talked about this already, but don't confuse histograms and bar graphs. Histograms are for quantitative data, and therefore the bar should be touching, and we can identify shape from them. Bar graphs are from categorical data, and they should not be touching. Those bars should not be touching because they're not representing a continuous number line there. And you shouldn't also try to talk about shape from a bar graph because what the order of the bars are is arbitrary. Don't use counts in a frequency table or percents in a relative frequency table as data because you have to talk about them in relation to what it is, the variable that you're talking about there. Use percents instead of counts when you're comparing. And just because a graph looks nice doesn't mean it's meaningful. We have to make sure that what it is we're looking at actually has value. So that's it for this lesson. Hopefully you have a better understanding of the 3 different types of graphs we talked about, dot plots, stem plots, and histograms, and have a decent idea about what it means to describe a distribution and comparing distributions. All right, that's it. See you guys next time.